In this unit, which is unit 8, we will derive information theoretic lower bounds for different problems. So far, what we have seen in the course is we saw uh, various motivating operational problems, okay, for definition of uncertainty, for definition of information. And as an answer to those problems, we discovered quantities like entropy, mutual information, KL divergence, and total variation distance. So we discovered those answers, but basically we just gave a scheme for those problems which attain these quantities, okay, which somehow brought in these quantities in its performance. Later we studied different properties of these quantities in abstract, and that was sort of just a mathematical section where we saw how these quantities can be manipulated. Now now we come back and continue with the initial questions that we have set up, the operational questions that we have set up, and do something for which information theory is actually very well suited. We derive lower bound. So information theory is a very powerful tool for deriving lower bounds or establishing fundamental limits. So what are these fundamental limits that we are talking about? When you define a problem, when you come up with a scheme for that problem, that scheme has some performance. Uh, but what is to say that some other scheme cannot beat this particular scheme? Well, to show that, you have to derive lower bounds for performance of the scheme, so, of that problem, showing that no scheme can beat those lower bounds. And information theory is very well suited for deriving such fundamental lower bounds. All right. So in this week, and in particular in this lecture, what I'll start with is I'll try to derive. I will derive lower bounds for a problem that we saw for compression. So remember how we defined a compression problem. I'm sure you have all forgotten most of it by now. So I'll revise it in one line. Okay. So for us, the compression problem was abstracted in terms of this quantity, L epsilon x. X was some random variable. Epsilon was a parameter between 0 and 1. It was defined as, it can be defined compactly as the minimum number of, so it's the minimum number of bits required to represent x when you want to recover it with probability of error epsilon. More precisely, it is the minimum of the log of cardinality of a set in bits, such that this set S is a subset of X and it has a probability exceeding 1 minus epsilon under S. Okay, that's what this L epsilon X is. Minimum number of bits required to represent this source X, such that the answer is correct with probability 1 minus epsilon. So the way to think of it is that all you need to do is store all the elements in this set S which attains this minimum, because this set S has large probability, and you can ignore all the elements outside it. Okay. So what we saw, this is some quantity that we wanted to understand, and what we established was an upper bound for this. We gave a scheme which showed that this L epsilon x is less than equal to lambda, okay, for any lambda such that probability that if you look at the set, of those values of x for which minus log px is less than equal to lambda, sorry about this, it's less than equal to lambda, so look at all those lambda for which this set has probability exceeding 1 minus epsilon. The minimum over all such lambda is an upper bound for L epsilon x. Okay, and in fact we gave a good estimate for this minimum. We said that not for the minimum, but we said that one good estimate for such lambda for which this bound holds with large probability, a good estimate for such lambda can be obtained using Chebyshev's inequality. So by Chebyshev's inequality, this such a lambda, one choice of such lambda is h of x plus square root of variance of the random variable minus log px. This distribution of x is under p, and p is also the PMF, okay, by epsilon. Okay. Okay. So this is one choice of lambda which works. So we said that, okay, so looks like entropy enters this answer, ignoring the small error part, which depends on epsilon. So, but entropy is the leading term here in many cases, in particular for IID distribution, and therefore this L epsilon x was less than equal to Hx. Okay. Now, how good is this bound? Okay, that's what you want to understand. Is can we do? We said that entropy therefore controls this L epsilon x, but we never justified it very formally. So, can we improve this bound? So now we will use Fano's inequality to show that this upper bound is actually almost tight, in the sense that you will see entropy also entering in the lower bound. Okay, that's what we will show now. Okay, so we will show that L epsilon x cannot be too much smaller than the entropy of x. Okay, that's what we will show now. So how do we show this thing formally? So to show this bound formally, we first note an alternative expression for L epsilon x. Instead of defining it in terms of sets, we want to define it in terms of mapping. So we claim that L epsilon x is actually minimum over all L, such that you can find or there exists mappings f from x to L bits and a mapping phi from L bits to x. So this is roughly the inverse of f, which you will apply to recover f, such that the probability that x is equal to phi of f of x is greater than equal to 1 minus epsilon. So is the claim. I hope the claim is clear. Instead of talking in terms of sets, now we are talking in terms of this mappings f and phi, which you can think of as a mapping f used to encode x into L bits, and then a mapping phi which is used to decode those L bits back to x. And what we want is that this decoded value coincides with the original x with probability greater than 1 minus epsilon. The minimum over L over all such pairs of mapping f and phi, I'm claiming is exactly equal to L epsilon x. So how do we show that? I'll give a rough proof of this. I think I had mentioned this before. Whenever you see an inequality like this, you should imagine two parts. You should imagine an upper bound and a lower bound, and you would like to show that both of them coincide. So let's first try to show that this L epsilon x is less than equal to this minimum L. So which means that, or maybe the other way around. Let's try to show that L epsilon x is greater than this. How do we show that? So what you have to show is that given any mapping f, you can find a set S such that S satisfies probability of S is greater than equal to 1 minus epsilon, and L, this L here is equal to log of cardinality of S. So how do we show that? So suppose you have, okay, so how do we show this? So first consider any mapping f from x to this and another mapping phi from okay, and for this mapping now we'll define that and of course we assume that x equals to phi of f of x with probability greater than 1 minus epsilon. So let's define S as the set of those x for which everything works fine. So it's those x for which these are all deterministic mappings. Phi of f of x, the decoded value when x is encoded, is exactly equal to x. Okay, so x for which everything works fine. And then by this property here, it follows that probability that x belongs to S is greater than 1 minus epsilon. So this S has large probability. Furthermore, we will now count the number of elements in S. Okay, so since f can take at most 2 to the power L values. Okay, and phi is and the elements x and s are actually phi of f of x. This can take at most 2 to the power L values. Therefore, phi of f of x can take at most 2 to the power L values. It's a mapping of something, and this something can take at most 2 to the power L values. So phi of f of x can take at most 2 to the power L values. So they can be at most 2 to the power L different values of x and s. We obtain this. Okay, and so this part here implies that the second property we want it log of cardinality of x is at most. All right. So you were able to find an S which has probability greater than 1 minus epsilon and has cardinality less than S, L. So for any mapping F here, you can find a set S here with large probability with cardinality less than L. Okay. And therefore for the minimum also you can find one such S. Okay. So L epsilon tilde x, which is this right side here. So if you look at the minimizing mapping, you can find one S which does this is greater than equal to log of cardinality of S for some S, some set S defined this way, such that probability of x in S exceeds 1 minus epsilon. But then this is some S, so the minimum S can only be smaller, so this is then greater than L epsilon x. So we have shown one side, we have shown that this guy exceeds this guy. Now we have to show other side, we have to show that this guy also exceeds this guy. To show this, for each S, we have to now construct a mapping F. Okay, so suppose S satisfies probability that x belongs to S exceeds 1 minus epsilon. Now let me define this mapping fx, which is equal to something, some special symbol, let's call it bot for error, a bot symbol, if x doesn't belong to S, and it is equal to I if x belongs to S. Okay, so what does it mean? I have basically enumerated all the elements of S. I'm assuming that S equals to x1 x L minus 1. I'm just assuming this L is defined so that the cardinality of S is this. Now for such an S, so this mapping F then, not L minus 1, I should use some capital L minus 1. Okay, then this mapping F takes values from X to L. It takes L possible values, one for bot and then this L minus 1 values. Therefore, F is a mapping from X to 0, 1 to the power log of L. Okay, so this is 0, 1 to the power log of cardinality of S plus 1. Seed of that. Actually, just let's do something else. Let's not define a bot when error occurs. We don't care what happens in this case. We are ready to admit any error. We'll just call it 1 again. Okay, so these elements, we basically allow them to collide with 1. Okay, so it doesn't matter. So then in this case, we save something. These are just cardinality of S elements. And now what is phi? Well, phi is very simple. When I see a number between 1 and L minus 1, which is stored here, I just declare x of I. So I'll be correct for everything except when I see 1 and actually the x was not coming from S. So in this case, probability that x is not equal to phi of f of x. This error can only happen if x does not belong to S. Otherwise, I'll be correct. And this has probability less than epsilon. Therefore, the L for this mapping exceeds log cardinality of S. Since this S was arbitrary, going over a argument similar to the previous one, what this says is L epsilon x tilde is greater than L epsilon x. Okay, so we have shown these two different, L epsilon x is greater than epsilon tilde. Okay, so we have shown two different inequalities. One is this one, which says that this one is greater than this one, then the other one is this one. And therefore they must be equal. And that basically completes the proof that this guy is also another expression for L epsilon tilde x. Okay, so basically this looked like something different from what you wanted to show, but I thought I'll complete this proof also. It's a small technical step which is needed to proceed. All right, so we can work with L epsilon x or L epsilon tilde x, doesn't matter. We'll work with this guy for lower bound. Okay, so we have now derived a lower bound. We still haven't shown that lower bound. All right, how do we show that? So now for the lower bound, we can just consider any mapping. Consider a mapping f from x to 0, 1, L and phi from L bits to x such that probability that x is equal to phi of f of x exceeds 1 minus epsilon. And let m be the message that you store, f of x, and x hat be the estimate that you decode, phi of m. So just draw a quick picture here. So you have x, use this mapping f, you obtain m, use this mapping phi, you obtain x hat. All right. So since uniform distribution maximizes entropy, this L must be greater than the entropy of this message m. This message m takes at most 2 to the power L values. But m is a function of x, right? Actually, let's do it this way. So this m, once you have m, from it you can take out x hat. So this one, h of m, is this minus h of x hat given m. Use chain rule here. But since x hat is a function of m, this guy here is 0. So you're just left with this guy. But this guy here is h of x hat plus this guy here is h of x hat plus h of m given x hat. Okay, and this term here is greater than equal to 0 because entropy is non-negative. So therefore this is greater than equal to h of x hat. This small part of the proof here is a very standard property. We note that x hat is a function of m, and then we can show by data processing inequality that h of x hat, a function of m, must be less than h of m. Okay, entropy only reduces when you apply a deterministic function. So this is just a deterministic function. All right, so we are here. Now, how do we continue from here? So from here what we notice is that x hat is actually, so we do this part. It will soon become clear why we are doing this. This is further greater than equal to h of x. Adding one more random variable only increases entropy. You see, I'm now using many properties like chain rule and non-negativity of entropy, left, right, and center. And that's why it's very important to get comfortable with those properties. But once you are comfortable with those properties, these kind of magical things are done. These arguments are essentially essentially justifying how the randomness can be split into different parts, and based on that, they are deriving some bounds. Okay, so this is true, and then h of x. This is a different color for different steps. So this part now, you need to think what this part is. So what happened here? How do we get this? Well, this thing here is just Fano's inequality. Okay. So since this holds for any L, this implies it also holds for the minimizing L. Okay. And that minimizing L is L epsilon x. We already argued that L epsilon tilde x is same as L epsilon x. So this is L epsilon x. So this must be greater than hx minus epsilon log cardinality of x minus 1 minus 1, let's say. Just bound this by minus 1. Actually, I'll be wasteful. Okay. So that's the lower bound we have derived. So very nice. Basically, we see entropy also in the lower bound. So entropy shows not only in the upper bound here with an extra variance correction, it also shows up in the lower bound with an extra correction which depends only on the log of cardinality of the alphabet. Okay. So in this sense, this entropy bound is tight. In fact, Shannon considered an asymptotic version of this question. So what is this asymptotic? What is an asymptotic version? So here everything is single shot. You see one symbol x and you want to store it and then you recover the symbol x. But typically in practice, you see a sequence of symbols. And as we discussed, a good model for a sequence of symbol is this memoryless source, the IID source. So for IID sources, we are interested in characterizing. So suppose instead of x1, x, you see this x1 to xn, which are generated IID from a common distribution P. For such sources, we are interested in characterizing the rate at which L epsilon grows with n. Okay, so we are interested in characterizing limit as n goes to infinity of 1 by n L epsilon x1 to xn. Okay, and this limit we can give it a name. Okay, but instead of this, we also want this limit for vanishing error. Let epsilon also go to 0. By the way, it is a little bit complicated to believe that this limit exists. Okay, but this epsilon going to 0 part can also be easy to argue, because as epsilon, because this function here, this limit here is a monotone function of epsilon. Anyway, so if you don't worry about limits, this quantity here is the asymptotic performance in vanishing error and with the length of the sequence going to infinity. Shannon wanted to characterize this quantity R star P, and we will now apply our bounds to obtain a very sharp characterization of R star P, the asymptotic rate, the asymptotic number of bits required to be stored per symbol for vanishing probability of error. So we now apply our bounds and get this tight expression for R star P. Okay. So how do we do that? First, from our upper bound, is L epsilon x1 to xn for IID x1 to xn is less than equal to entropy of x1 to xn plus square root of the variance of minus log p x1 to xn. Now I'll just abbreviate this with xn by epsilon. Now note that minus log pxn is equal to summation I equal to 1 to n log pxi. So this is a sum of IID random variables, and therefore its variance, this is some property which is very important. We saw it in the first few lectures. This variance is also equal to sum of individual variances. Okay, it's the sum of variance of minus log px1. Okay, so this is some bound for the variance. Okay, so when I substitute this bound here, what I get is L epsilon x1 to xn is less than equal to so again x1 to xn are IID, therefore its entropy of x1 to xn is just n times entropy of x1. This is the additivity property of entropy plus okay, this is what we get when we divide by n and take limit n going to infinity. What do we get? One by n L epsilon x1 to xn. This first term remains, but the second term, because we only have a root n here, in the limit as n goes to infinity, this becomes 0. Okay, so we get that this limit is bounded by this for every epsilon. Okay, so we get a bound like that. Also, we have derived a lower bound, so we apply now this lower bound to our L epsilon term, L epsilon x1 to xn term. So remember that we have shown that L epsilon x1 to xn is at least, so here is our lower bound, h of x minus epsilon cardinality of x minus 1. Okay, so h of x now is n times h of x1, because again x1 to xn are IID, minus epsilon times log cardinality of x. But now this, for the sequence, this cardinality grows like this. There's a minus 1, but that doesn't help us much, so I just remove it, and then minus 1. So this is n times h of x1 minus epsilon n log x minus 1 by n. So if you divide by n and take this limit, this guy is greater than equal to h of x1 minus epsilon log cardinality of x. Yeah, this is slightly informal because you can just think if this limit exists or not. But actually making this formal is not very, it's straightforward actually. So you just need to introduce lim sup and lin-winf, notions of lim sup and lin-winf. And then at the same time, we will show that this limit exists as well as these bounds coincide. Okay, so this bound holds for a given epsilon. So now what we are interested in the limit as epsilon goes to 0. So what happens when epsilon goes to 0? The error goes to 0. Well, that's the interesting part. This error term here vanishes, and so you have h of x1. Okay, so this bound here implies r star p, the optimal rate, is less than or equal to h of x1. This bound implies that r star p is greater than equal to h of x1. If it's less than equal to h of x1, it's greater than equal to h of x1, then it must be equal to h of x1. And this is the main result here. And this has a name. It's called Shannon's source coding theorem, which holds for IID sources and for this specific setting. So in English, what this says is that the number of bits per symbol that is needed, let me put h of p here, the number of bits per symbol that is needed to store an IID source with common PMF, common distribution p, with vanishing error is exactly h of p. This is exactly h of p. So we have not only shown a scheme which attains this, we have also shown that no other scheme can improve over this. So in this specific sense, at least, entropy is the optimal answer. It's the unique optimal answer. Okay, and so the way we obtained it is slightly different. We actually derived single shot lower and upper bounds here, and then we took limits to get this bound, the tight bound. Okay, so this is the first lower bound that we want to discuss in this unit. In the next lecture, I'll derive another lower bound for a different problem, namely for the hypothesis testing problem. So basically, we'll derive a matching lower bound for Stein's lemma. We didn't do this proof earlier. Okay, see you in the next video.